elastoplastic torsion. Now, now we have several assumptions even to uh, look into the uh, elastic deformation part of it. So, for example, it should be a uniform, the shaft should be an uniform cylinder. Homogeneity, then isotropy. Homogeneity means everywhere it's the same material, and isotropy means in each direction it has the uh, same stiffness. So all of those assumptions go into deriving certain equations of torsional deformation. But here we would not make ourselves concerned with deformation. Um, the bottom line here is that I'm just exaggerating the cylindrical cross section. So, so imagine before deformation, I drew a straight line on the boundary of the cylinder, okay, and then I applied some torsion. Then I applied some torque. Okay, so imagine this end is fixed. Okay, so the torque coming from it is from the fixed support. Okay, so let us draw the free body diagram. So I'm getting rid of the support. Uh, so imagine this is the center of it. So what happens is that this is a radial line, let's say, before the deformation, and once it deforms, okay, due to torsion. So let's say this is the same line that I drew on the surface has now become tilted, and that tilt angle itself is our shear strain gamma. Okay, uh, so now that shear strain is essentially, let's say this is the length of the cylinder, then let's call this arc as small ab. Okay, so this is the length of the arc. So limit gamma tends to 0. Okay, um, gamma equals is it is actually gamma is approximately equal to tan gamma, which would be AB, the arc length AB divided by L. So you are supposed to take this arc length, this curved length. Okay, so so you need to understand that typically the shafts are uh, slender members. Okay, wherein this radius, the outer radius, let's call it R0. So R0 is actually much smaller compared to L. In a situation like that, okay, this so-called angle of twist, okay, So that is the angle that it produces at the center of the cross section. Let's call it phi. That need not be tiny. Um, you see, AB is R0 R0 times phi, the arc length. Okay, so this phi need not be infinitesimal. The phi need not be so small, but as long as this strain gamma, okay, is less than 5 degrees. Now what is 5 degrees? 5 degrees would be 5 by 120 times pi in radian. Okay, so it's pi by 36. Okay, which is not a small number. I mean, it's a small number, but it's not infinitesimally small. I mean, pi by 36 is actually greater than 1 by 12, which is around this much. Okay, so as long as such relation is true, okay, we can treat gamma as a small angle. How small is that gamma equals tan gamma and sine gamma. Okay, so that small, we can imagine it to be that small. So so the strain, you need to understand that if I talk about gamma in terms of angle, okay, this is small enough angle to have gamma equals tan gamma. Okay, this value right here. But as we have discussed so many times, that the elastic limit of strain is around 10 to the power minus 3, and 8% strain is definitely well in the limits of plasticity. Okay, so in terms of strain, when you treat gamma, the shear angle, as shear strain, that essentially is not quite the small strain. Okay, so the strain itself is huge, so we can use that relation in the elasticity and plasticity. Okay, next thing is, let's look at a smaller radius, somewhere r less than r0. Within the material, actually I can draw this circle with solid line. Okay, so there is this cylinder, and on that cylinder, because the radius of that cylinder is r less than r0, you see this angle of twist phi is the property of a given section. For the fixed section, that phi must be 0. Okay, but at the end surface, that is the maximum. That's how you are producing the twist. Okay, I gave wrong direction to the torsion here. Yeah, no, actually correct one. Okay, so now on the circumference of that smaller circle, the arc length, let's call it a prime and b prime. Okay, so that a prime b prime is actually r times phi. You see, on the circumference, I chose a location arbitrarily. I drew this line arbitrarily somewhere on the circumference, somewhere on the outer surface. Okay, so it basically shows that since phi is a property of the cross section, okay, and length and outer radius are pretty much, same, so the shear strain, okay, is constant on the circumference. The shear strain is constant on the, not the circumference, the outer surface. Okay, I mean, you can go to a smaller length as well. Okay, but there you would be encountering a smaller angle of twist. Okay, so let's say you are over here at L by 2, you'd probably be seeing a 5 by 2 of angle of twist, but that's okay, because you see gamma then would be R0 times 5 by 2 divided by L by 2, which is R0 pi divided by L. It's only when you change the radial position within the cross section that you get a different expression for the gamma. Now we are writing the strain, shear strain, as a function, as a function of radius, and that just turns out to be r times phi. You see the length is still the same, right? L. Okay, so that quantity is r0 phi by L times r by r0, or in other words, let's call this gamma as gamma 0, the maximum shear strain, which is at the circumference when I'm talking in terms of the cross section. At any internal radius, it is simply this ratio. Okay, so much like bending, where the axial strain, or the the normal strain, was directly proportional to the height, irrespective of whether you were in the domain of elasticity or plasticity. In this case also, the shear strain is directly proportional, okay, to the radius. Okay, irrespective of whether the deformation is taking place within the elastic limit or not. Actually, couple of assumptions go into there. Okay, so in the so the statements are, let's say r0 remains a constant. That means because of torsion there is no change in r0. Then statement number 5 is plane sections remain plane, which is to say that if I take a section right here, okay, which is a plane, let's say before deformation, it doesn't deform into this. Okay, or in other words, there is no warping. What is warping? Warping is the deflection. Let's say the axis is z axis. So warping is the deflection in z direction as a function of the coordinates in the cross section. Okay, so the plane sections remain plane. Okay, next is distance between planes remain same, which is if I were to take planes which are perpendicular to axis, couple of planes, okay, the distance between the two doesn't change, which is to say that the length also doesn't change, the total length also doesn't change. And next comes the most important assumption: rigid rotation of cross section. Don't get confused with the term rigid here. Okay. What it basically means, if a cross section, okay, acha, one more thing, cross section remains circular. Not only the plane sections remain plane, the sections also remain circular. Okay, and their distance between the two planes are same. Okay, the radius doesn't change at all. Okay, the size of the cross section doesn't change, the length doesn't change. Okay, and and the section remains a plane, and it does remain a circle. Now, if it remains a circle, okay, imagine before deformation, I drew this imaginary lines on the section. Okay. Now this is what happens post deformation. If it is twisted, these perpendicular lines, okay, remain perpendicular straight lines. They do not become something like this. Having that would not be rigid rotation. Okay. So every single section rotates rigidly, but it's not that the entire structure is rigid. Okay, because every cross section is rotating with respect to the a cross section which is slightly uh, or infinitesimally below or above it. Okay, so with respect to this cross section, let's say this cross section, the bottom face is fixed, the top face rotates, right? So however, the cross section rotates rigidly, but it does rotate with respect to the other cross sections, and that's what gives you the shear strain. Okay, so all of these assumptions go into getting this expression right here, and this is important. Okay, now when you are within the elastic limit, then the shear stress is proportional to shear strain, which basically means it is okay, tau max times r by r0, where tau max is the shear stress at the circumference. Okay. Now, I have the urge to ask you, this shear stress, which shear stress is it? Okay, is it tau xy, tau yz, or tau zx? Okay. But the thing is, I'd not be asking you this question because, uh, in my experience, I'm not going to get the correct answer. Okay. So, answer to that question is, we'll have to look at on which surface is that shear stress taking place. Okay. So this is a surface which is perpendicular to Z axis, but the shear stress is not acting along X or Y. If this is the radial line, it is actually acting perpendicular to that, which is to say it is acting in the theta direction. So the section is perpendicular to Z and the stress is acting in the theta direction, okay, tangential direction. So the tau you are talking about in this case is tau theta z or tau z theta. Okay. So for tau z theta, you'll have to look in the surface. Okay. Which is perpendicular to theta direction. That means, let's say, if I extend this radial line and take such a section, okay. So in that, your your that surface would be perpendicular to theta. Okay. So the shear stress is acting in that plane. Okay. So then the shear stress on that surface would be acting in z direction, and that would be tau z theta on a plane that is perpendicular to theta direction. And this one is tau theta z. Okay. If I were to draw the shear stress situation, okay, on the circumference or on the outer section. Okay, so let's say I took two planes that are perpendicular to z direction, and then two more that are perpendicular to theta direction. Okay, so on this section I have this differential r d theta, r0 d theta, and dz element. Okay, and in that element you have this shear stress situation. Okay, which means that that at 45-degree angles to that, that means along this direction and along this direction, we will have the principal stresses. Okay, so so in other words, if you were to take an element which looks like this, okay, so in this direction you have sigma 1, where sigma 1 is tau theta z, and then you have sigma 2, which is compressive and has an expression minus tau theta z. Okay, so let's say if you have a brittle material which you are subjecting to torsion, let's say a piece of chalk. Okay, so cracks tend to open in these two directions. Okay, so if I draw that portion of the cylinder, okay, if there is a crack which is aligned like this at right angles to sigma 1, which is that is parallel to sigma 2 direction, it would have the highest potential to open. Okay, now if I continue extending this line on a cylindrical surface, that would be forming a helix. And that's why, so that is the line along which the cracks open, that actually forms a fracture line. Okay, and that's why when the cylinder fractures, or so you can imagine this is what is happening. When the specimen fractures, this is what the geometry looks like. So let's say this, and this extends. But as soon as these two fracture line, I mean the two ends of the fracture line come close, it is kind of, uh, you know, they rapidly join each other. Okay, so that is how the fracture surface is formed in a brittle material under torsion. Okay, but we need this expression where we can relate between the shear stress and the radius, and that is valid within the elastic limit. Okay, but you'll have to again relate that to the applied torsion to the system. Okay, and it's a known exercise. I mean, you already know the final expression that tau max is for a solid cylinder 16t by pi d cube, pi d0 cube. But I'm not going into that. I mean, I'll be going into that, but through the derivation. Okay. So we need to derive that quantity because we don't have the expression for the plastic deformation part, and we need to identify the method in which one should do that. So, so the idea is this is your section, okay, and let's say you are this much away, r less than r0, away from the center, and you take a differential area dA, and in that differential area dA, you have this shear stress acting normal to the radial direction, which is tau acting on it, okay, and tau of r acting on it, okay, and that produces a differential force of tau times dA and a differential moment about the center, which is r tau dA, okay. So so when I integrate that moment, that actually is the response to the applied torque, okay, and that actually is actually supporting that applied torque and keeping the object in equilibrium, okay. So therefore this quantity has to be equal to the applied torque, and that torque must then be, you need to substitute the expression for tau r then. So tau max comes out of the integration, okay, uh, and then 0 to r0 to twice pi r d theta dr. So 0 to r0, r d theta dr. This is the differential area dA, okay. Then there is r for taking moment, and then you are substituting the expression for tau, which has another r. So total of r cube, okay. Now, since the limits on the integrations are independent of one another, you can separately do the integrations. So what I can do is tau max divided by r0, integration 0 to twice pi d theta, and 0 to r0 r cube dr, which basically gives me twice pi tau max r0, and then r0 to the power 4 divided by 4, and eventually r0 cube. So that gives me the expression for tau max, two t by pi r0 cube. And if you substitute r0 equals d0 by 2, you are going to get the familiar expression. Okay. Now that's what happens within the elastic limit. Okay. Now imagine your material is not uh, infinitely elastic. It has certain limit to elasticity, and that limit is the yield stress, beyond which it becomes perfectly plastic. So this type of constitutive relation is elastic, perfectly plastic. Okay. So what will happen? The slope of, oh sorry, I just put wrong stress and strain. So what will happen uh, when the elastic limit ends? So in the bending, or in the 3-point bending, we saw that that the plasticity, okay, starts at the cross section, at the outermost layer of the cross section, where the bending moment is maximum. That's what we saw in bending. But what happens in torsion? Is there a particular cross section? In bending, we saw that there is a particular location where the bending moment is maximum, and that's where your if you low increase the load proportionally, okay, so that's where you get your first yielding, first plastic deformation. Is there such a location in torsion? তোমাদের প্ল্যানটা কি পুরো সেমিস্টারটা এরকম মুখ বুঝে থাকবে নাকি?
না
So in torsion, sorry, কি বললে?
8টা আননট হবে।
আটটা আর নট হবে। প্রশ্নটা বুঝতে পেরেছো কি জিজ্ঞেস করছি এতক্ষণ ধরে? Of course, the stress is maximum at the circumference in the cross section once you have a given cross section. But that was true for bending as well. That if in a given cross section, plasticity would start or yielding would start from the outer layer. I'm not talking about a particular cross section. I'm talking about where in the geometry. Is there a particular cross section? Where is there a cross section where the yielding starts first? যেমন bending এ there was a location, there is a single section where the bending moment is maximum, okay, and we know the yielding starts in that section first, okay.
স্যার আউটার লেয়ারে স্যার সার্কুলার সেকশন আউটার লেয়ার।
আরে বাবা, একটা প্রশ্ন কেউ বুঝতে পারে না, কিন্তু বাংলায় বলছি তাতেও বুঝতে পারছো না? প্রশ্নটা শোনো, কথাটা শোনো আরেকবার। আউটার লেয়ারের প্রশ্ন নয়, ওকে, আউটার লেয়ারের কথাটা তো বোঝাই যাচ্ছে যে the stress is highest at the circumference. My question is there a particular cross section যেখানে you have the higher stress than any other cross section, much like bending? In bending, you have the highest bending moment at a single section, and that is a section which produces highest bending stress at the boundaries compared to any other section. My question is,
ক্রস সেকশন থাকবে না টোটাল।
কোশ্চেনটা শোনো, in torsion do we have such a section?
না স্যার।
So in torsion, actually, as we discussed, the shear strain doesn't change with the axial position. We showed that whether we are at L or L by 2, it's the same shear strain provided we are at the same radial location. And because the strain is not changing along the length, so is the stress. That is, the stress is also not changing along the length in the elastic limit, because in the elastic limit the stress is simply proportional to strain. So no cross section is different from the other, okay. So when it comes to torsion, we can look at any arbitrary cross section, okay? And theoretically with all the assumptions, okay, we are also not considering the end effects. That is, let's say the assumption number 9, because in the end you simply don't apply moment, right? There would either be a gear mechanism or anything, so you apply a couple, a set of forces, okay. going in and out. So or maybe multiple set of forces. Okay, so immediately after the boundary where the load has been applied, the stress state is exactly not this one. Okay, because it has the end effects. Okay, it's not that that very nice looking moment that we show that is being applied over here. That moment comes into place through let's say a set of distributed forces, or uh, you know uh, maybe coming from the gear and so on. Okay, so which are not necessarily that uniform moment. Okay, and because of that, mm, I mean, this and this are equivalent to one another. Okay, when you have a rigid body to work with, but it's a deformable body, you are considering its deformation. Okay, and unless you go a little bit inside of the geometry. Okay, by inside I mean along the length, you are not going a straight state quite like this. Okay, so that is also another assumption. But in that portion of the geometry where it can be assumed to be like this, there is no quote unquote favorite cross section. There is no cross section which has more likelihood theoretically of having the first yielding compared to others. Okay, so we don't have to bother about where do we get the maximum bending moment, or which cross section. We don't have to ask that question. Okay, but once we are in a given cross section, it is obvious that at the circumference the yielding starts first. Okay, and then you have the expression. Okay, so can you tell me what is the value of t when yielding starts at the cross section, when you have the yielding for the first time in the cross section? Can you tell me the torque required for that?
tau yielding into pi r cube by 2.
So at that time, the tau max, or let's call it tau 0, which is tau at r0, that has to be tau y. That's when the yielding first starts in the cross section. And we have already mentioned that has the following expression. So that way, it is simple to identify how much should be the torque value. Okay. So let us call it T prime. Now, what happens um, to the cross section when the torque applied is more than tau prime? You see, the shear strain is still changing the way it was changing with within the elastic limit, which is gamma is gamma 0 times r by r0. Okay. So this much is your gamma 0. Okay, so strain is still proportional to, okay, I shouldn't be drawing this negative side of it, because there is no negative shear strain, it's positive. Okay, because you see, there is no positive and negative side of theta direction. Okay, you just simply take perpendicular to radial direction, so it is just the top triangle. Okay, So you can see shear strain is changing proportional to radius. And this is the relation between shear stress and shear strain. Elastic, perfectly plastic. Okay. And shear strain is changing linear to R, proportional to R. Okay. So how would shear stress change with the radius? How does shear stress change with the radius? This is how shear stress changes with shear strain, and this is shear strain changing with radius. Okay, which is proportional. So how would shear stress change with radius?
linear.
সরি, লিনিয়ার? এতক্ষণ গতকালকের ক্লাসের পরে তোমার মনে হচ্ছে এটা লিনিয়ার হবে? So there would be, if t is greater than t prime, there would be an elastic core and a plastic shell. Within the elastic core, let's say the core radius is C. In that, the shear stress is linearly changing. And then in the outer shell, it is constant because it is elastic, perfectly plastic. So the strain is proportional to radius. It's as if radius is the scaled down version of the shear strain. Okay. So the stress changes with the radius the same way it changes with the shear strain. So you have this much shear strain. Okay. Now let's say for a given elastic core, okay. So let us try to get the expression for the shear stress. So that should be tau y times r by c if r is less than c, and equals to tau y if r is greater than c. So we already described this dm was r tau dA, and dA was r d theta dr. So the torque would be integration 0 to r, integration 0 to twice pi r tau r d theta dr. If I'm putting the limits on theta inside, I should be doing the integration with respect to theta first. But then in a circular cross section, this integration with respect to r and theta, they are kind of, the limits of the integration are kind of independent of one another. So what I can basically do is I can simply take this thing outside. I mean, simply independently do the integrations and simply multiply them. So tau r squared dr. Now this part of the integration simply gives you twice pi. So everything interesting is with the other part, the integration with respect to r. Now that integration could be split into two parts. One is the integration between 0 to c, and then the other one is from C to R0. Okay. Now substitute these expressions for tau of r. Tau is a function of r. Substitute these expressions, okay, and get the expression for this t over here. So determine the moment required to produce an elastic core of size c.
So 2 pi tau y into R0 cube bracket R0 by 4c plus 1/3.
Is it the expression?
Yes, sir.
I think something is missing. No, no.
So that would be c cube by 4.
It's not going to be okay. It's going to be c cube by 4, right? Okay.
Yes, sir.
In the earlier expression, where you are supposed to do it between 0 to r0, so it would be tau max. So t should be tau max by r0 times twice pi, then integration 0 to r0 r cube dr, right? And that should be r0 r0 cube, sorry, no, by 2. So my point is, I have written this expression wrong. It should be actually by 2, right? Divided by 2, isn't it?
Yes, sir.
Okay. Acha. So this is the expression when you are producing an arbitrary elastic core of size C. Okay. Now this actually becomes a function of C. I mean, that's how we get the mathematical expression. That's how it is simplified for us to calculate. But logically speaking, C is actually the function of T. Okay, so the size of the elastic core depends on the applied torque. Okay, so but this is how you get the expression. Okay, so next thing is get the expression for T when C equals R0. Substitute C equal R0 and get the expression for T. What expression do you get?
Pi into tau y into r cube by 2.
Is it
By
T
2.
prime? Is it T prime?
Yes, sir. Yes, sir.
Sir.
Okay, which shows that your derivation is consistent. Okay, acha. So the next question that we would like to answer: what is the maximum torque that you can apply to the shaft, or what is the maximum torque bearing capacity of the shaft? How do you answer that? You see, if the entire section has turned into plastic, okay, so it is entirely tau y. Then the shaft cannot take, being elastic perfectly plastic material, the shaft cannot take any further torque, which means the size of the elastic core has reduced to 0. Okay, as long as there was an elastic core, okay, you can apply more and more torque, so there was some non-zero stiffness. Okay. and uh, and the moment you reached this you reduced the elastic core to 0, there is no further torque bearing capacity. It has reached its limit. Okay, there is a maximum limit of the torque that it can withstand. Okay, so this corresponds to C equals 0. It is quite obvious, right? The elastic core, the size of the elastic core was initially R0 and then it gradually reduces. Okay, so substitute C equals 0. What expression are you getting? The maximum torque that you can apply to the system, which is T double prime,
2 by third
is
pi.
is it the expression?
Yes, sir.
And is this quantity greater than T prime? Half versus 2/3. Half of this quantity and 2/3 of this quantity. Okay. So you see, when the torque is half of tau y pi r0 cube, okay, the plastic deformation has not started in the section. And by the time it has reached from half to 2/3, by that the entire shaft has become plastic, and the entire cross section has become plastic, and the cross section cannot bear any further torque, just going from half to two-third. And if you check, divided by T prime would be four-third. That is one-third, increase in torque, and the material cannot withstand any further torque. Okay. Now we'll stick to these expressions. Now we do not know uh, what is the value of C. In the earlier two examples, we looked at the two extremes. The plasticity has not started. The entire cross section has become plastic. Now, for an arbitrary C, this is the expression. And we would, do the unloading exercise and get the residual stresses for this arbitrary size of the elastic core. Okay. So remember, for an arbitrary elastic core, this is the expression for the torque. And that torque must be elastically unloaded. Okay. So you need to find out what is the stress equivalent. What is the stress equivalent, okay, of that torque, and then, elastic stress equivalent of this torque, and then you'll have to subtract that elastic torque from this expression. Okay. So the elastic stress equivalent elastic, if this torque could be applied within the elastic limit, if this torque could be applied within elastic limit, it has to be tau C, put this expression, then by pi r0 cube. Then anywhere in the section, at a given radius r, it would be twice Tc times r. Okay. So substitute the expression for Tc. Okay. And this expression, okay, remains same for, because the unloading is elastic, okay, everywhere. So this expression remains the same for both the parts, the part that is, above C and that is within C. Okay, for both the parts, this is the expression for the equivalent, the equivalent elastic stress of this torque right here. Okay, and that actually is unloaded. And if you are forgetting what are the logics and all, you should revisit Monday's lecture. So tau r would be tau y times r by c minus, so this is the residual stress once the complete unloading of the torque has been done. So the torque, there is no force, no moment in the system, but there is still residual stress. So that is going to be this quantity, and substitute the expression for Tc. Okay, and this is your assignment. R equal, let's say, 10 millimeter. Tau y, let's say, 84 megapascal. R0 is 10 millimeter. This one is 84 megapascal. Okay. And C is R0 by 2. Okay. So I need you to plot tau residual versus R, where R is between 0 and R0. Okay. So make a plot in Excel sheet. So that is your assignment for the day. So the idea is that with the elastic core, this one was the stress distribution. Okay. So in this is the stress distribution in a loading phase. In the unloading phase, in the unloading phase, this is the elastic stress equivalent. In some places it is higher than the elastoplastic stress, and some places smaller. Okay. So this is the elastic equivalent of the applied torque, that is the torque required to cause certain amount of elastic core. Okay. So if that torque could be applied uh, without crossing the elastic limit. Okay. Because in unloading you have this twice tau y window, okay, of elasticity. So you can do that actually. So this is the stress that needs to be recovered. So this stress that is to be recovered is actually higher than the actual stress that has happened in loading in some regions, and in some region it is actually smaller. So in the end it forms, so this green must be subtracted. So once this green is subtracted, you get a stress state like this. All are shear, some are going negative in theta and some are going positive in theta. Okay. So this type of shear stress distribution do you get? Okay. And that's what I'm asking you to plot. Okay. So I think I'm done with today's class. In the next class, we will talk about thick cylinders. Okay.